All right, this is for Math AH. We're going to do lesson 8.1A. So if you have your PDF typed, printed out, or you have electronically, or you have a piece of paper, let's be ready to go. Number 1, Jane takes a survey of 100 random students to determine what color of eyes they have. The results are shown below on the chart. So everybody answered blue, brown, or green. Based on the outcome of the survey, what is the expected probability of picking a student with green eyes? So here we're doing experimental probability because we had a survey. So we did an experiment and we're seeing what would the probability from our data. So we have data in this thing. We have to add up our total. So our total, 30 plus 55 plus 15 is 100. So we know that in our denominator we have 100. And we want green. So looking at our green, we have 15. So our probability of green is equal to 15 out of 100, which we can reduce. Those are both divisible by 5, so we get 3 out of 20. B, if there are 40 students in our next class, how many would you expect to have green eyes? So we're going to take our answer from before, 30 out of 20. We've got a ratio, but this time our total is going to be the 40. So we're putting the 40 on the bottom. And we need to solve the proportion. So you could cross multiply or scale up. I think this one's pretty easy to scale up. I know that 2 times 20 is 40. So this is 2 times 3, which is 6. So I get that x is equal to 6. So I expect 6 people to have green eyes. I would expect 6 people to have green eyes. Okay, so today we're going to introduce compound and independent and dependent events. So compound, when we make something a compound, that means we're putting things together. So compound just means that we have 2 or more events. Now, my 2 or more events can either be independent or dependent. Independent means that the 2 events do not affect each other. So maybe I have a spinner and I have a dice. What happens on the spinner has no effect of what's happening on the dice. So these are 2 events that do not affect one another. Okay, dependent events affect one another. So maybe I'm going to draw twice from a bag. But after I draw from the bag, I'm not going to put my thing back. So maybe my bag has marbles and I have 10 marbles and I draw one out and I put it in my pocket. Well, now the next time I draw, I change the bag. There's no longer 10 marbles. There are 9 marbles. So the first thing I did changed what's in the sample space for the next thing. So here, the 2 events, one of the events has an effect on the other. One of the events has an effect on the other event. Okay, and we'll be talking about these a little bit more when we go along, and we'll come back up to this definition. Okay? So here, a marble is drawn and then replaced. So if I have a bag of marbles and I take one out to see what it is, but then I put it back, am I changing the bag for the second draw, or is it the same bag? So we would say, hey, that's the same bag. So this is independent because we see the word replaced. That's a good thing to put up here. So keyword here would be replaced. The opposite of replaced is without replacement. So keyword for dependent is without replacement. Those are two things we're going to be looking for. Okay, so here in my bag, it has 1 red marble and 3 blue. 1, 2, 3 blue, and 1 red. Okay, it says, what is the probability of getting a red and then a red? So I see that I have 2 things that I'm doing. 1, 2. So from fundamental counting principle that we did in module 1, I know that I have 2 different things I'm going to have to multiply. Each time there are 4 marbles in the bag because I'm putting back what I took out. The first time I go to draw in the bag, I have a 1 out of 4 chance of pulling a red. The second time I go to draw in the bag, I still have a 1 out of 4 chance of getting a red. So in total, I have a 1 out of 16 probability. Okay? So when we have independent events and it says P of, I'm losing my pen here, P of A, then B, I can just do the probability of A times the probability of B. Okay, next one. Probability of red then blue. So again, I have 2 things that are going on. 1, 2. Each time, because I replaced the marble, there's 4 things in the bag. My chance of getting a red the first time I pull is 1 because there's 1 red in the bag. And then my next time I want to pull a blue. Well, there are 3 blues in the bag. So when I multiply that, I get 3 out of 16. Okay? A blue, then a blue. Each time there's 4 in the bag because we're replacing. The first time there's 3 to replace. The next time there's 3. So this is 9 out of 16. Okay, moving on. Fill the blanks for calculating the probabilities of each independent compound event. Independent. The first one doesn't affect the others. That was important. Compound just means we have more than one event going on. Suppose we call the first event A and the second event B and the third event C. If probability of A is 0.5 and probability is 0.5, what's the probability of getting A and B? So then we're just going to multiply our 2 numbers. So 0.5 times 0.5, or a half times a half, is a fourth, so 0.25. Okay, it says A, then B, then C. We can have a bunch of events. We're just going to multiply our 3 probabilities. So here we're going to go 0.5 times 0.5 times 0.5. So we have a half times a half, we know is a quarter, and half of a quarter is an eighth. So here we get an eighth, or 0.125. Okay? Use the rule in the prior question to calculate the probability of getting a head, and then a tail, and then a head, and then a head, and then a head. All right, so I have 1, 2, 3, 4, 5 flips. 1, 2, 3, 4, 5 flips. The first time I want a head, there is a 1 out of 2 chance of getting a head. The next time I flip a coin, there's still a head and a tail. I didn't change the coin. So then again, I get 1 out of 2, and then 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 1 out of 2. I have to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I put too many 1 out of 2s. I should have 5 of them. Okay, so then I'm multiplying that. So this is really just 1 out of 2 to the 5th power, which is 1 out of 32. All right, number 8. Suppose you have an unfair coin where the probability of getting heads is 0.8 and the probability of getting tails is 0.2. Compute the following. So if I want to do head times tail, my first one's a head. The probability of getting a head is 0.8. And the probability of getting a tail is 0.2. And when I multiply those, I get 0.16. Okay, go ahead, pause the video, and fill in the next three. Let's check that you know how to do it, and then play and check your answers. Okay, so here I had to multiply my two numbers. I got 0.16. Here I'm multiplying the probability of head times the probability of tail times the probability of head. I get 0.128. Here I'm multiplying probability tails times tails times tails. I get 0.008. Compare the calculations that are used for a fair coin and an unfair coin. How are the calculations and how are they different? Well, we're still using the same method. We're multiplying each of the events, but what the probability individually are different, so we get different answers. So here, grab the text box. We still multiply the same number of events. However, the individual event probabilities are different. All right, moving on down. A card is drawn at random from those shown below and is replaced. So always got to pay attention to that word, replace. That means we're doing independent probability. Replaced. Okay. What is the probability that both cards are blue? So I always want to pay attention to how many total cards there are. So when I look at this, I need to know, okay, there's a total of 20. Okay. So both cards are blue. I want blue and then blue to happen. So I have two events that I'm multiplying. Each event is 20 on the bottom because it's replaced. Then I have to count how many blue cards there are. So when I look up there, there are 5 blue cards. So I'm taking a blue card out. I have 5 chances to get a blue card out of 20. I replace it. So the next time I still have 5 chances to get it done. I like to reduce. That's 1/4 times 1/4, which gets me 1/16. Okay, next one. The probability that neither card is red. Okay, so I'm still doing 2 cards. So I have over 20, over 20. And now I want not red. So how many not red cards are there? Well, there are 15 that are not red. And then again, 15 that are not red. I like to reduce. That's 3/4 times 3/4. So that is 9/16. Okay, what is true about all independent compound events? The first event's denominator doesn't get changed because the second event's denominator did not get changed because of the first event. The denominator of the second event did not get changed because of what happened in the first event. All right, scrolling down. Find the probabilities of the dependent compound events that are described below. Write your answer in simplest form. A bag contains 4 red M&Ms and 6 blue M&Ms. Once the M&M is drawn, it's eaten. The person has no patience and just eats it. So that means the next time I draw, there's less in the bag. Okay? So at first, there was 4 red and 6 blue, so there were 10 in the bag. But we didn't put it back after we drew it, so the next time there's not 10 in the bag, there are 9 in the bag. So the first time we had 4 out of 10 chance for getting a red. We ate the red, so now there's only 3 reds and 6 blue. And we want to pull one of the blues. Well, there's 6 blues to be pulled. So here I am going to reduce. So my 6 and my 9 reduce to 2 over 3. My 10 and my 4 reduce to 2 over 5. And when I multiply that, I get 4/15. Okay, next problem. I want probability of a red and a red. So the first time I go to draw, there are 10 in the bag, and there are 4 red. I grab a red out and I eat it. Now there are not 10 in the bag, there's 9 in the bag, and there are not 4 red in the bag, there are 3 in the bag. Now I'll go and work my numbers and reduce them. So 3 goes into 9 3 times. 4/10 reduces to 2/5. So I get 2 out of 15. All right, next one. I want a blue and a blue. So the first time I go into the bag, there are 10, and there are 6 blue. But once I take out a blue, I eat it. So now there are 9 in the bag and 5 blue. I need to reduce my fractions. The 6 and the 9 can reduce. The 2 and the 5 and the 10 can reduce. The 2's reduce out. So here I get 1/5. Sorry, that's not right. 1/3. All right, I want you to go and try the next problem. So pause the video and try the next problem and then check your answers. Okay, so there was 3 out of 8 and then 1 out of 7. Nothing reduces, so I got 3 out of 56. Here I had 4 out of 8, then 3 out of 7. The 4 and the 8 reduced, so I got 3 out of 14. Here it wants me to get a green and a green. Well, are there 2 greens in the bag? There's not 2 greens in the bag, there's only 1. So here, I don't get a chance of getting a green and green. That doesn't exist. So we had 1 out of 8, 0 out of 7. That gives me a 0 chance of getting 2 greens. Okay, so next one. A bag contains 3 red marbles and 5 pink marbles. The marble is drawn and is not replaced. I can't eat, well, I shouldn't eat the marbles. So instead of saying eaten, it says not replaced. But that's the same type of problem. So the first marble is red, so I have to pay attention. How many marbles in the bag? I got 3 plus 5, so there are 8 marbles in the bag. And there are 3 red. I take out a red and I don't replace it. So now there are 7 in the bag, and there's still 5 pinks in the bag. So I have 3 8s times 5 7ths. I'm looking for things to reduce. Nothing reduces. So I get 15 out of 56. All right, go try B and C. All right, check your work. Here I got 3 out of 8 and then 2 out of 7. I reduced and I got 3 out of 28. This one had 3 events, no problem. I had 3 out of 8, then 5 out of 7, then 2 out of 6. I reduced the 2 and the 6. I reduced the 3 and the 3, and I got 5 out of 56. All right, moving down the page. Letters are chosen at random at the same time from the word triangles. One letter is drawn and not replaced. So we got to pay attention to that. It's highlighted, it's bold, it's underlined, it's important. Not replaced means we have dependent events. The second letter is drawn. Find the probability of the events described. So first, I have to count up the total letters in triangles. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know that there are 9 letters the first time. And then the second time, because I didn't replace it, there are 8 letters. So our denominator here is 9 and then 8. Both letters are vowels, A-E-I-O-U. So there's 1, 2, 3 vowels. I took one out, I didn't replace it. So the next time there are 2 vowels. I reduce my fractions. 2 goes into 8 4 times. 3 goes into 9 3 times, so I get 1/12. both letters are consonants. Well, the consonant is the opposite of a vowel, right? So here we had 9, and then we had 8 because we did not replace. Both are consonants. Well, if there's 3 vowels and there's 9 total letters, that means there's 6 consonants. We kept one. We didn't put it back. The next time there would be 5 consonants. Then we need to reduce. The 6 and the 9 reduce. That's 2 and 3. And we get 10 over 24, which means I didn't reduce all the way because that would not be reduced. The 2 and the 8 reduce. That makes a 4. So then I get 5 over 12. That looks much better reduced. So 5/12 chance of getting a constant and then a consonant. What can you say is true about all dependent compound events? The first denominator, what happens, the not replaced, changes the second denominator. So here, the possible outcomes for the second event are changed by the first event. Okay, so we saw the denominator decrease. Next section. Are events A and B independent or dependent? Oh, and my sheet lost some. Oh, no, I didn't. Okay. I thought it lost some fractions. It didn't. My first event, a nickel comes up heads. And then B, a penny comes up tails. So does flipping a nickel change the penny? Does a nickel's flip change a penny? And I'm going to say no. So I'm going to say they are independent. The flip of the nickel does not change the penny. Okay, so I want you to try number 19 and 20 and 21, and then come back and check your answers. Okay, so for 19, I got dependent. If you get a 6 on the red cube, then it limits what you can get on the other cube. You have to get a 6 on the blue cube. 20, dependent because the marble's not being replaced, so it changes what was in the bag. 21, independent because the marble is being replaced. Okay, so let's scroll back up to our prior definitions and let's talk about them just a little bit more. So here we had the probability of A and then B. When it's independent, we can just multiply the two independent probabilities and don't even think about them. And the next one, the notation for it is a little bit funky. So here, if we want probability of A and B, probability of A, then B, we take the probability of A just like normal. We don't change it. But then we have to think about the probability of B. So we call that probability of B once it's changed by A. So this is B after A changes it. Okay, so maybe there's less in the bag, so you have to drop the denominator down or something like that. But that is the notation for that. It is the probability of A times the probability of B after A changes it. All right, scrolling back down the page. Now we're going to talk about exclusive events. Okay, mutually exclusive and inclusive. So we talked about how mutual meant more than two or more. Exclusive, they cannot happen at the same time. Inclusive, they can happen at the same time. So, events that cannot happen at the same time. And we'll add a little bit more to this later. And this right here, events, that can happen at the same time. Okay, so let's just go try some and then we'll come back once we've seen a little bit to clean up the definition. Circle mutually exclusive or mutually inclusive for each event. Find the probabilities selecting one card from the standard deck without jokers. So we got a deck of cards here. There are 4 suits. These are not called the clovers. They're called the clubs. Okay, and the spades and the hearts and the diamonds. Sometimes aces counts as 1. Sometimes it counts as high cards. Just depends on the game. So here, probability of picking a king or an ace. So first thing we have to decide is there such thing as a king-ace card? Is there a card that has a king and an ace? Then we go, no. Here are the kings, and here are the aces. Those are 2 totally separate things. So those are exclusive. So we would circle exclusive. Okay, and then when we have exclusive, we can just add up our totals. So we can do probability of king, when we see the word add, or we're adding, plus the probability of getting an ace. So there are 4 out of 52, or 1 out of 13 kings. And there are 4 out of 52 aces, because there's 52 total cards in the deck. That gives us 8 out of 52, which reduces to 2 out of 13. Okay, so let's go up. So when our thing is exclusive, we are just going to add our things. So we would just do probability of A or B equals the probability of A plus the probability of B. Okay, let's go look at another one. The probability of king or red. Okay, well, here I see the kings, and down here I see the reds, but I have to pay attention. I can't double count the red kings. So here, this is inclusive because it can happen at the same time. So I'm going to count my kings. There's 4. So the probability of a king, there is 4 out of 52. Plus the probability of red. Half the deck is red. So there are 26 out of 52. But what happens if I just add them? There are not 30 cards I would be happy with. I counted these 2 cards when they were kings, and I counted those 2 cards when they were reds. So I have to take away the probability that it's a king and red. So I have to take away 2 out of 52 because that's what I double counted. So I get 28 cards out of the 52, which means I'm happy with 7 out of 13 cards. Okay, so going back up to our definition, when it's inclusive, we have to pay attention a little bit more. We have to do the probability of A or B. We go ahead and we find the probability of A, and we find the probability of B. But what happened is we double counted it. So we have to subtract out the probability of A and B, because you were double counting cards if you just added. Okay, moving on down. I erase my circle up here. Okay. A 4 or a heart. So you have to think, is there such card that's the 4 of hearts? And I say, yeah, there is the 4 of hearts. So both can happen at the same time. So I know it's inclusive. So I'm going to get the probability of getting a 4. There are 4 out of 52 cards that are 4s. Plus the probability of getting a heart. There are 13 out of 52 that are hearts. But my problem is I counted the 4 of hearts here, and I counted the 4 of hearts here. So I have to take away one of my double counts. So minus 1 out of 52. And if I wanted a heart, any of these cards, or a 4, any of these cards, that means I would be happy with 16 out of 52 cards, which is the same as 4 out of 13. Okay, see how I double counted this one? That's why I had to subtract that 1 out of 52. All right, so why don't you try 25, 26, and 27. Pause the video, and then we'll check back in. Okay, so here, a number smaller than 5 or a face card. Well, if you're smaller than 5, you're not a face card because aces are not face cards. They don't have faces on them. The one that has faces, they actually have people on them. So here, smaller than 5, that's the 4, 3, 2, 1. There's 16 of them, 16 out of 52. Face cards, that's the Jack, Kings, and Queens. There's 12 out of 52. So I add them up. 28 out of 52 reduces to 7 out of 13. A 5 and not a diamond. So can that happen at the same time? I'd say, yeah, it could be like a 5 of spades, okay? Or a 5 of hearts would work. So I have inclusive. There are 4 5s in the deck. There are 39 cards that are not diamonds. But then I have to pick the 3 cards that are 5 and not diamonds. So I get 40 out of 52, which is 10 out of 13. Last one, a face card or a club. Now that can happen at the same time because I can have the king of clubs or something like that. So face cards, the one with the faces, the Jack, Kings, and Queens, there's 12 out of 52. The clubs, there's 13 out of 52. But then I have to take away the face cards that are clubs. There are 3 face cards that are clubs. So I take away the 352 that I double counted. I get 22 out of 52, which is 11 out of 26. All right, Math AH, we are done with lesson 8.1A. So now you can go do your homework.